Today, we're diving into one of the most famous scientific theories in human history. But, we're not just going to sit here and crunch numbers. We're going to look at the theory of general relativity as if it were a living, breathing character. A character that was praised, completely forgotten, and then miraculously resurrected. But most fascinating of all, it's a theory that was nearly killed by an impossible, logic-defying monster of its own creation. So, what exactly happens when a scientific theory predicts a monster that its own creator completely refuses to believe in? It sounds like pure sci fi, right? But this is the central mystery of Albert Einstein. The undisputed genius of the 20th century violently rejected the darkest, most extreme conclusions of his own life's work. His math revealed this terrifying flaw in the fabric of the universe. And instead of accepting it, he spent years desperately trying to prove his own equations wrong. To understand how that happened, we first have to understand how he built this universe in the first place. Section 1. Gravity Reimagined. To get a handle on this, let's travel back to 1907. Albert Einstein was just sitting at his desk in the patent office in Bern, Switzerland, when he had what he'd later call his happiest thought. This single flash of insight would radically alter our view of how the universe works and completely dethrone Isaac Newton, who had pretty much owned the realm of gravity for 250 years. Okay, to really grasp this, we need to talk about the equivalence principle. Einstein realized that if a person were in free fall, they actually wouldn't feel their own weight. Gravity essentially disappears as a result of its own effect. Imagine dropping a capsule in a giant vacuum tower. A feather, an apple, a heavy weight, they all float perfectly weightless right next to each other as they fall. Einstein saw this and realized, wait a minute, gravity isn't some invisible magnetic pull. Instead, think of space like a giant block of jelly. When you drop a massive object like a planet into it, the jelly distorts and curves. Matter is literally bending the very geometry of space and time around it. Think about Newton's universe for a second. For centuries, scientists believed space was just this flat, rigid stage, and time was a huge, universal ticking clock that passed exactly the same way everywhere. But Einstein's universe is a massive paradigm shift. It's a curved, four-dimensional geometry. And here's the real kicker. Time actually slows down the stronger the gravity gets. There is no universal clock. Every galaxy, every solar system has its own localized time. Section 2. Proving the impossible. Now, having an incredible thought experiment is one thing, but proving it mathematically, that's an entirely different beast. Einstein needed to figure out the exact gravitational field created by objects in this curved space. To pull that off, he had to rely on his mathematician friend Marcel Grossmann, whose notebooks on geometry helped Einstein navigate these seemingly insurmountable mathematical walls. Einstein worked like an absolute monomaniac for 8 grueling years to finally translate this curved universe into an equation. Let's track how this rapid-fire timeline actually played out. In 1907, we get that initial spark of inspiration. By November 1915, Einstein finally cracks the equations, and he knew he had it right because his new math flawlessly predicted a tiny quirk in the orbit of Mercury that Newton's theory simply couldn't explain. But the definitive proof? That came in 1919. A British astrophysicist named Arthur Eddington traveled to an island off the coast of Africa during a solar eclipse. Why? To photograph distant stars and prove that their light literally bent as it traveled through the curved space around our sun. When those results were presented to the Royal Astronomical Society, the tension in the room was unreal. Eddington stood up right in front of a portrait of Newton and dramatically proclaimed, "Galilei made a universe which lasted 1,400 years. Newton also made a universe which has lasted 300 years. Einstein has made a universe, and I can't tell you how long that will last." Overnight, Einstein was catapulted to global superstardom. But there's a really funny thing about that fame. Einstein was suddenly the star of Parisian salons, traveling the globe in the 1920s, but almost nobody actually understood his theory. I absolutely love what Charlie Chaplin famously told Einstein at a movie premiere. "They're cheering us both, you because nobody understands you, and me because everybody understands me." Section 3. The black hole problem. And this is where our story takes a genuinely dark turn. Picture this. It's 1916, right in the thick of World War I. Einstein receives a letter from a German soldier named Karl Schwarzschild. Now, Schwarzschild had done the titanic work of calculating the exact space-time distortion generated by a star using Einstein's equations. But hidden deep in that math was a terrifying anomaly. It raised a question that is honestly chilling. Does the world end in an equation? Schwarzschild's solution exposed what came to be known as the Schwarzschild singularity. To Einstein, this wasn't just abstract math, it was a monster. It described a sphere, an impenetrable black bubble hidden inside stars, where the very concepts of space and time simply cease to exist. Let's break down the math of this monster, because it's wild. At the center of this theoretical object, the radius, or r, becomes exactly zero. You're left with a point of infinite density, which causes gravity to become infinity. The result? Space and time completely break down. They stop making sense. In fact, during a conference in Paris, a mathematician named Jacques Hadamard actually stood up, pointed threateningly at Einstein, and used this exact math to say his whole solution falls flat on its face. It was literally the edge of the world, hiding right there on the chalkboard. So here is the crucial turning point. How did Einstein react? Well, he just flat out didn't want to believe that a star could cave in and implode to zero. There is something deeply unbearable about it to him. So he wrote what scientists today consider his worst paper. He desperately used flawed logic to try and disprove the existence of the singularity, because he stubbornly refused to accept what his own math was telling him, and because the math was so incredibly difficult to grasp in the first place, the physics community practically abandoned general relativity. For decades, it became this forgotten fossil. Moving into section 4, vindication in the stars. Einstein passed away in 1955, still doubting the monster hiding in his equations. But in the 1960s, astronomy went through a massive technological revolution, and suddenly, his greatest work was brought back to life in the most dramatic way possible. Because, as it turns out, nature absolutely does create the extreme conditions Einstein thought were impossible. Let's look at the real-world life cycle of a dying massive star. First, the star swells up. Next, it depletes its nuclear fuel, meaning gravity wins the tug of war and it starts to shrink. Step 3, the core collapses in on itself. And finally, the outer material violently blows off, leaving an intensely, unbelievably dense core behind. 10 kilometers. Just think about that number for a second. You have the mass of a billion, million tons, literally the mass of our entire sun, crushed down into a ball just 10 kilometers across. And this isn't just theory anymore. In 1967, a brilliant young British scientist named Jocelyn Bell Burnell noticed a curious pulse signal while observing the night sky. She had discovered a pulsar, which was quickly identified as a rotating neutron star. The remnants of these dead stars were totally real, and they were creeping dangerously close to that impossible singularity Einstein had feared. And then came the ultimate mathematical proof. In 1964, mathematician Roger Penrose was literally just crossing a street in London when an idea hit him out of nowhere. He figured out a way to characterize the collapse of a star that had gone past the point of no return. He called it a trapped surface. His math proved definitively that light on both sides is focused completely inwards. The star has absolutely no choice but to collapse down to a point of zero radius and infinite density, a black hole. Time at that singular point completely stops. Einstein's monster was undeniably real. Just to vividly picture what this gravity monster actually does, we have to talk about spaghettification. Because the gravity gradient is so staggeringly strong near these objects, if you were falling in, the force pulling on your feet would be massively stronger than the force on your head. You would literally be stretched out like a piece of spaghetti until your body is pulled apart piece by piece as you drop onto the star. So yeah, definitely not a healthy vacation spot. Section 5, the next great mystery. Okay, so general relativity works. Black holes exist, but science never rests, right? The discovery of the black hole actually exposed an entirely new frontier of physics. What exactly happens at that tiny, infinitely dense center where the fabric of space-time completely tears apart? See, we're facing a massive cosmic clash right now. On one hand, general relativity is absolutely incredible for describing the infinitely large. We're talking gravities, stars, entire galaxies. But the center of a black hole? That is intensely small. And to understand the intensely small, you need quantum mechanics. Currently, scientists are struggling to unite these two massive fields of physics to figure out what happens when the incredibly large meets the incredibly tiny. It is a puzzle that is still unsolved today. Let's look at one really fascinating attempt to solve this puzzle. Carlo Rovelli's theory of loop quantum gravity. Rovelli suggests that, hey, maybe the star doesn't actually crush down to absolute zero. Instead, it shrinks to a ridiculously tiny point called a Planck star, and then immediately bounces and explodes back out in a matter of milliseconds. So, why don't we see these tiny explosions everywhere in space? Because of Einstein. Remember, extreme gravity radically slows down time. So, that millisecond explosion happening deep inside the black hole, seen from the outside, from our perspective, it happens in super extreme slow motion, taking billions and billions of years. It's just an incredible cosmic illusion. Which brings us to a question that is guaranteed to keep you up at night. Is time just an illusion? Ravelli's equations, the ones attempting to merge gravity and quantum mechanics, are incredibly special because they don't contain a time parameter at all. Think about that. It suggests time might not even be a fundamental ingredient of the universe. Einstein completely revolutionized how we view space and time, but looking at these mysteries still waiting inside a black hole, you really have to wonder, what will the next grand theory reveal about the true nature of reality? Thanks so much